Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back. Students, basically, I will start a new lecture that is related to the method of analysis of slab system or any frame system. Okay. So in this method, in this lecture, basically we are covering the equivalent frame method. Clear? And this is the one of the most important method, which you can say this is an ideal method, which can be applied to any kind of structure. Basically, as we in previous lecture we will see that I will cover direct design method, approximate method, and so many methods. Okay, so let me show you the methods which is basically used to analyze any given structure. So these are the a group of methods which is basically used to analyze any kind of structure. We have elastic analysis, and then we have plastic analysis. In elastic analysis, basically in our usual practice we uses elastic analysis. Plastic analysis, basically it is also an approach which is the most accurate approach, but it is very difficult to practically implement this method. Although we will use the non-linear pushover analysis through ETAB, but there are also some other difficulties. So that why basically in usual practice elastic analysis are basically used, because the plastic elastic analysis also take, it is also a very time consuming method, because when you are facing a very complex project, you have to run the analysis and it will take too much time. Okay. And sometimes our computers do not support such kind of structures which is complicated and complex. So whatever, we have these two major methods. Okay. And in elastic analysis, basically these are such approaches in which we can say the Hooke's law is applicable. Okay, we basically apply a load and a structure, and it will give us a bending moment, shear and stresses, something like that. Okay, but in plastic analysis, basically we have to model. First of all, we have to prepare a model of a structure. Okay, and then we have to draw stress strain curve or the capacity curve. Okay, and we have to put that curve in our system, and then basically our system, the structure which we are going to analyze, basically our system or computer basically compare that present model with that actual structure capacity, and then the capacity curve will be drawn and it will be checked. Okay, so this is a complicated method. Okay, but this is the most accurate method because it uses the inelastic behavior or inelastic capacity of a structure. Although in our practice, basically we will use this method. So the elastic method is further classified into exact method and approximate method. So up to this point, basically we will cover these two methods: ACI coefficient method, and which is also approximate method, and a direct design method, point of reflection, total frame analysis, which is used for lateral loading. Clear? Now in today's lecture, basically I am covering the finite element method, slope deflection method, distribution stiffness method, equivalent frame method. This is our today topic, which inshallah I will cover it in 3 to 4 lectures. There will be some examples I will do. Okay, and before starting this method, I would recommend you to please go to my YouTube channel, and in my YouTube channel I have uploaded uh, this lecture series which is related to direct design method. If you do not have any concept about the direct design method, then it is very difficult for you to understand the concept of equivalent frame method, because equivalent frame method is not a complete method of analysis of any structure. It just only transform a system from a 3D to a 2D. When then we transform a 3D structure to a 2D structure, then we analyze that system by moment distribution method or slope deflection method, or whatever the method which is available, the exact analysis method we implement. And then in the final stage we use the direct design method coefficients. Okay, so the rest of the procedure is same as the direct design method. So that's why basically I recommend you to watch this. Total there are 15 lectures which is completely explain the direct design method, whether they are beam supported slab, whether they are flat system or flat slab system. Okay, So a complete set of definitions and examples are covered. Basically I will cover the same example here, but before I'm going to equivalent frame method, I recommend you to please watch those lecture series. So let us start basically that the basic concepts of equivalent frame method. Okay, this is, remember, equivalent frame method is an exact, sorry, first of all I would like to share you my documents which I'm using to mm, that I'm preparing my lecture. Okay, the first one is this example. Okay, this is basically an example by structure point. Okay, concrete subfra solution, and then I'm using McGregor ACI code with some other notes. Okay, and there is my one of the research thesis. Okay, this is the lecture by Ali in Atya. Okay, this lecture is also very important lecture relevant to equivalent frame method. Clear? Similarly, I am using Nelson book, McCormick. Okay, and reinforce design of tall buildings by the Tarrant, a very important, most famous book. Okay, which is used for high-rise structures. This book is very important book. Okay, it is also very it also defined the equivalent frame method in very detail. Okay, Wang Salmon, it is a very important book for concrete structure. Okay, and the last one is the Mosley. Okay, this is basically, this book is written in Eurocode, but it also clarifies some basic concepts. Okay, if you are uh, familiar with Eurocode. Okay, so let's start. I have written my own notes, I prepared. Okay, what is basically an equivalent frame method? It is a procedure which transforms a 3D frame to a 2D frame. This must be remembered. Okay, uh, basically, for example, let me show you here. Where is that notes? This one, I think so, this one. Okay, so you see we have different types of structures, slab system. We have beam slab supported system, we have flat slab system, we have flat slab system, we have all these two group categories in waffle and bandwidth slab system. So remember, the DDM method or the approximate method, there are some limitations. Okay, for example, if you are using DDM method, there are certain ACI limitations. If you are using approximate coefficient in the ACI coefficient method, there are certain limitations. If those limitations doesn't fulfill, then we are compelled to use equivalent frame method, because equivalent frame method is such a method which have no limitation, you can say. This is the basic advantage of equivalent frame method, which is an ideal method. It can be used for every structure. Okay, so that's why it is very necessary for every student, you must learn this method. Okay, and let me show you one of the important concept of equivalent frame method. This is similar to basically one of the DDM method concept. Okay, in this system what we have basically do, let's say let us we have this kind of structure you see here, and this is a 3D frame system. Clear? No, if you are just, let's say you extracting this interior frame. Okay, and this interior 2D frame you see, and modeling this in 2D frame into a tape or a shape, this is a wrong practice. Okay, first of all, if you are going to extract any 2D frame from a 3D frame, there must be a procedure, there must be some procedure through which explain basically how to extract a 2D frame from a 3D frame. Equivalent frame method is that procedure which basically explain how you can extract a frame from a 3D system and how you will convert that 3D frame system to a 2D frame system. Once you convert, once you transform that 3D frame to a 2D frame, then and you find the basic requirements like stiffnesses and torsion stiffnesses, etc., then you are allowed to model that 2D frame into a shape or a tape that is the best practice, that you extract the frame, 3D frame from a 3D frame, okay, convert that 3D frame to a 2D frame and then model that 2D frame into a shape or a tape. This is the best approach. Clear? And today basically you will see how to extract a 3D frame and transform that frame into a 2D frame. So as we did basically in our DDM method, we basically extract the exterior frame, the interior frame in east to west direction, and similarly in north south direction. Two frames basically we, if the limitations are fulfilled. Clear? So you see basically here we see the interior frame. So what will be the middle strafe, column strafe? Okay, you already know if you are knowing the concept of DDM. In equivalent frame method, basically what we do, we basically select one of the interior frame and one of the top frame, okay, if the heights of the frame is similar. Remember, if the heights of the frame is similar and there is no other such kind of variations in the frame, so we just, you see here, we select this ground story frame. Now the concept is that in equivalent frame method, we convert this slab system to a horizontal member, which is known as, in equivalent frame method, known as slab beam system. So a slab beam system, whenever we are using an equivalent frame method, this means that this is the horizontal member. We basically convert this slab to a horizontal system, a horizontal member. If there is beam, let's say, so we will find the combined stiffness of the beam and the slab and convert them just into a line member. Clear? Similarly, this, you can see this column. The column is also converted to an equivalent column. Equivalent column is such a column whose stiffness is less than the actual column. Clear? So you will see the definition of these terms. Okay, let me share those concept. Okay, here we see this is a 3D frame to a 2D frame, and finally the 2D frame is analyzed by the moment distribution and any other technique to get the member moments or shares. Okay, EFM is not a complete method of analysis. It is just a transformation technique in which we use moment distribution for analysis of members and distribution of members moments obtained by DDM are already explained this. Okay, now DDM having 6 limitations. If those limitations is not fulfilled, we could not use DDM, but the EFM have no such limitations. This aspect of EFM dominate, okay, over the DDM. But if limitations is fulfilled, then DDM is simpler over. This is very important point you must remember. If the limitations of the DDM is fulfilled, there are certain 6 to 5 limitations of DDM method. If those limitation is fulfilled, then it is better to use DDM as compared to finite equivalent frame method, because equivalent frame method involves some other lengthy calculations as compared to DDM method and give also same results as those by the DDM. But if those limitations are not fulfilled, then we are compelled to use EFM. Clear? The complete procedure will be explained in examples. One must know the basics and concept of the diet. How to implement this method, inshallah you will see this a complete example I have solved on EFM, which cover a whole procedure of EFM. But there are some basic concepts before we are going to use the EFM. What are those concepts? Properties of slab beam system I already defined. Okay, the horizontal member in the equivalent frame are referred to as slab beams. Okay, in equivalent frame basically what we have to do, we take a 3D frame system, convert them into 2D frame system, but in that 2D frame system the horizontal members are called slab beams. So slab beams, column capital, drop panels, okay, all these things are known as slab beams. This is remember. Also slab with a beam running parallel to the equivalent frame. ACI code section 13.7.3 explains how these non-prismatic beams are to be modeled for analysis. So there is a procedure, okay, because you see that whenever we are using, let's say you in this figure you see that the section of this frame within these two columns you see is changing. So these are non-prismatic members. The moment distribution method, which we basically taught in our bachelor's basically. So in that method basically we are using a constant EI, okay, a prismatic member. Here you see there is the section is different, section here is different. So due to this variation in the in between these two columns, we are compelled to use a technique, okay, which cover these variations, and the equivalent prime method is a technique which basically cover these variations. Okay, you see there is a column capital, there is dot panel, and there is slab system. So there is section is basically increase, there is an increased section, but here you see the section is decreases. So the section at AA is different, at BP is different, and at this point it is different. So that's why it is very important to understand these concepts. ACI code section 13.7.3.1 permits to use gross moment of inertia rather than using crack moment of inertia. This is also a very important point because you already know that the under portion of a tension member is always crack, and we do not consider that crack portion. For that purpose we need a crack moment of inertia. But ACI code here, because this it become very difficult to use the crack moment of inertia. We have to calculate for each section, and it basically complicate the procedure. So that's why ACI code permit you to use the gross moment of inertia, mean that you are allowed to calculate this section, total section, and here is total section, not just calculating that section which is uncorrect. Clear? So this is the example you see here. What is L1? L1 is the center to center distance. Remember, L1 is that distance, as if you are familiar with the DDM method. L1 is that distance which is the span length in the direction of our analysis, and L2 is the cross dimension. Clear? So this is a slab with drop panels, and here you see the variation basically in sections. Okay, here is the section is different, here is the section is different, and that's why EI is not remain constant. Here is EI1, EI2, okay, and to convert all those stiffness into an equivalent stiffness, we have to multiply, we have to divide each stiffness with this factor. So you will understand these things. Okay, variation in EI along the slab beam. Clear? Now here you see this is another section which is L2. Basically L2 is the cross or the transverse direction. So this is the slab. Okay, here the slab is uniform. Clear? And we need only one section. Clear? And here you see the section is non-uniform because here is a T section. Clear? With a drop panel. Okay, so this basically change the section property, and L2 is the cross direction. Okay, cross length. So here the section is different, here the section is different. So this is variation in section basically. EI values for a slab with a drop panel. It is very important. Variation in moment of inertia along the length shall be taken into account. Equivalent prime method basically it covers this variation. It covers this variation that here is the section is different, here is the section is different, and here is the section is different. So it has a greater stiffness as compared to this section, and similarly greater stiffness as compared to this section. So equivalent prime method covers this variation along the length. Okay, this is the main key point, remember. And ACI code basically explain. Thus for the slab with a drop panels shown in figure above, the moment of inertia at section AA is that for a slab of width L2, figure 1332. So already I explained this. Okay, here basically the section is this one which is different, but there the section is different, and here you see for that we have this section, but for slab we have this section. These things are a little bit boring, but you will understand in example, inshallah. And similarly, for a slab system, these are just only theoretical portions. You have to just read about this. Okay, here you see the section that when we have a beam slab system. Okay, basically equivalent frame method is very useful for a beam slab system. Okay, when approximate coefficient method is not applicable. You see here the section at CC, the section at DD. Okay, you see this is the depth of the beam. Okay, this is the beam which is running along the in that direction, basically, which is the north south direction, and this is the beam which is running in the east west direction. So what is H3, what is H2, and what is H1? Note down these things. Clear? What is C1? Basically C1 is the in the analysis direction. It is in the direction of L1, while C2 is basically in the cross direction. Clear? You will understand these concepts. So this is basically, now here you see the variation in stiffness. Here you see the variation in EI. Here EI is different. In the met section the EI is different, and here is the it is different. So you see we have a T section. Clear? Having a top length L2. The depth of this total section is H2, and this is HF. So this is very important. And similarly, you see L2 H3. Here the section is here. Clear? So that is the lower portion, you can say. Basically the main purpose of this diagram is to show you the variation in sections. Clear? You see I1 cross section used to compute I1 section at CC. Okay, here is the section. If you are calculating moment of inertia at this section, you will use T section. Okay, and at D, basically at D section will be used to I2. Okay, here if you are going to calculate your moment of inertia at this section, that is dt, so your section will be look like in this shape. You have to you can say L2H3 cube divided by 12. Clear? And EI values for a slab beam system. Now here you see this is a flat slab system with no drop panel, with no column capital, so there will be no variation in EI. So that's why I am recommend the above statement recommend you to use in such cases DDM method with if the other limitation is fulfilled. So this is the basically because there is no variation in the slab system. So here you see we have only one section which is calculate moment of inertia. Okay, L2HQ divided by 3. But in that beam slab system we have to use different sections. Clear? So the next thing is that a flat slab figure shows with column is shown in section D. The equivalent frame that will be used for the actual numerical calculation is shown. ECS modular elasticity of the slab. Okay, and with section 2 to a fictitious section is shown. Okay, approximately. So this is just a theoretical portion. An expression for I for the equivalent section is also given. In this expression, C2 is the width of the column in direction of the perpendicular. The gross moment of inertia at the face of the support is calculated and is divided by this factor. This is very important. So you will see these basic concepts. This approximates the effects of the large increase in depth provided by the column for the distance in which the slab and column are in contact. Up to this point, the whole key purpose of this whole discussion is that we have to calculate moment of inertia at different sections. Clear? And for that different section we have to use different cross sections. Like if you have a flat slab system without drop panel, your section will be look like in this shape. In that case, moment of inertia will be look like in this. Okay, but if you have a T slab system, then your moment of inertia will be divided by this factor, C2 divided by L2. What is C2 L2? That are the transverse direction. and this is the equivalent slab beam system, clear, which basically shows the stiffness is okay. And the next thing, inshallah, you will completely understand these concepts, what these theory basically, what is the basic purpose of this theoretical portion, clear. So at this stage I think it will also be very difficult for you people to understand these concepts. Let me give you some other example concept of columns, okay, that is the equivalent column basically, which is used in equivalent frame system. And in equivalent frame system basically you see that here we have a column, and in equivalent frame method basically we use the concept of transverse beam or a torsional member, which is known as torsional member. In this figure, what you basically see here, you see that there is a beam which is running transverse to the analysis direction. This is our direction of analysis, okay. Now this is the center line of the beam or a span, and this is the actual column. So why we are using equivalent column in equivalent frame system? Because here it's explained that this slab system is basically trying to rotate the beam in this clockwise direction, while the column basically preventing that slab system from rotation. So here basically what the basic concept is that there is production of torque. You can say there are torsional stresses developed. You see this distributed torque, okay, that is denoted by mt, and the torque which is applied by the column. So as the column basically prevent the slab from rotating, but the effect of column to prevent the rotation of this transverse member is basically is dominant in the near region of the column, but far away toward the center line of the panel it decreases. So that why the section will highly rotate. You can say there will be more torsional strains at point A and at point C as compared to B. This is the main key function, mean that there will be maximum torsional stresses as compared to this point, clear. So the whole theory is basically explained here. In the figure you see that a two-way slab system is supported by an H-beam, clear. The H-beam is also called transverse beam or torsional member, clear. L1 is the span length and L2 is the width of the equivalent. This is the equivalent ridge frame or interior frame. The width of this frame is known as L2, while the length of this frame is known as L1. Remember, you also see what is C2 and what is C1. C1 in the span direction, while C2 is in the transverse direction, clear. The column provides support to a small portion of the width of the equivalent ridge frame. This means that this column provides a support. It prevents the panel, it prevents the slab system from rotation, but it is up to a very small amount of width, okay, not to the full width, clear. Now mt is the distributed torque along the edge of the beam or torsional member. This torque is applied by the slab, and this torque is resisted by the resistance of torque mt provided by the column, okay, noting that the torsional member is rotated to a greater degree at C and A and C. Already I explained this as compared to section B. Owing to torsional deformation of the H-beam, clear. I already explained these things. This torsional deformation of the transverse supporting member reduces the effectiveness of flexure stiffness provided by the actual column at the support. So what is the key purpose of this statement is that remember, due to the rotation of this torsional member or due to the rotation of this transverse beam, what it basically did, it reduces the effectiveness or you can say the effective stiffness of this actual column, and due to that we use the concept of equivalent column. Equivalent column, you can say it is such an imaginary column which uses such a stiffness which is less than the actual column. Why? Because why not we use the stiffness of this actual column? The reason is that its actual stiffness is basically reduced due to this transverse effect, due to these transverse strands. Clear? So to calculate that stiffness, which is known as equivalent stiffness, we use this equation. Clear? 1 over KEC equals to summation of KC plus summation of 1 over KT. So what is KC, KT and KEC? You see flexure stiffness of actual column, torsional stiffness of the edge beam and flexure. You will understand these concepts, clear, in examples. Now these are the authors which basically first introduced the concept of equivalent column, clear. And how to calculate KT? This is the equation 9 ECSC L2 1 minus C2 divided by L2. So already I explained that you have to use this factor. Okay, EC is the modulus of elasticity of slab, C is a torsional constant, and you will see how to calculate this C value. Okay, here is the diagram. You see that the column bends, the torsional member bends in this direction. Here you see the twisting. This twisting is smaller as compared to this twist, and due to this kind of effect basically we use this KEC, that is the equivalent stiffness. Clear? Now see, this is very important term, torsional constant. It is a constant which basically account for this effect. Okay, you see this constant is calculated by dividing the cross section of the torsional member into subdivision, and you will see the calculation of C, but this time you must remember C is calculated by this equation where X is the smaller shorter side and Y is the larger side. Clear? This is remember. It should be noted that C recognizes the contribution to the stiffness of the torsional member in resisting the in-plane bending through torsion. This means that the transverse beam do not allow the slab beam to bend or rotate, and thus contributing to the stiffness of the frame, and that contribution is countered by the constant C. This is the key function of C. Okay, that the transverse beam or the transverse member, it basically what it did, it basically prevent the slab beam from rotating, or you can say from torsional deformation. So to recognize the importance of this torsional member, we use constant C. Okay, that C basically enhances the stiffness of the column. Clear? Now how to calculate this C? Okay, this is very important. A beam frame into the support, in the direction of analysis the torsional stiffness KT needs to be increased. KTA, this is very important. I will show you this. Okay, that what is KTA equals to KT multiplied by this factored ISB, moment of inertia of the slab beam divided by moment of inertia of the slab. This means that if, for example, you see here in this figure, that you see there is no beam. So in this case, you don't need to multiply KT with that factored ISB divided by IB. But if you have this system, this is our analysis direction. So if in our analysis direction, if there is any kind of beam present, you have to increase that calculated KT by multiplying that KT with ISB divided by IB. It is very important. Okay, I will show you this in examples. Clear? You have to use then KTA, not KT. Okay, so if is any beam present in the direction in the direction of the analysis. Clear? This is C. How to calculate a C? Okay, so a transverse section. Okay, this is our analysis direction, and this is our transverse direction. So in transverse direction, if you have a drop panel and plus slab and plus column capital, in that case this is our effective section, and this will be the depth of the transverse section, or you can say a transverse beam, and this will be the length. So this longer side will be our y and the shorter side will be our x. Similarly, if you have any no beam, so in that case this will be the transverse section. Its longer direction will be y1 and the shorter direction will be x1. If you have only drop panel, okay, a slab with a drop panel, so this will be your transverse section. Then this will be x1 and this will be your y1, remember. And similarly, for example, if you have an edge beam, so in case of edge beam, as you see here, okay, you see here in this example we don't have any beam system, clear? But for example, let me show you this one. You see, if this is our analysis direction, okay, yes, this one. So here you see, if this is our analysis direction, so this is our transverse member. So what will be the effective section of that transverse member? So it basically explains this concept, that this dotted portion is the section of our transverse member. And how to take these kind of values, this you see this cantilever portion will be HW or less than 4 HF, okay. And similarly here you have to use different options. Remember, we have same thing but option 1, option 2. In option 1, basically you see this is y2 and this is x2, and similarly this is y1 and this is x1. But here you see y2 is changed and y1 is changed, remember. So we calculate C for this option, we calculate C for this option, and we will select the maximum value in both cases. Remember, this is very important. Similarly, if you have a T section, so in case of T section we have two sections, remember, and a T section is also divided into two options. I will do some examples on it, clear? Here you see this is y2, you can also denote this by y1, and this is x2, you can denote it by x1. Similarly here this is our y2 and this is our x2. If this is y2, this one will be x2, remember. This is I think so, this is error, okay. Or you can say this is y2 x2, then this is y1 x1, clear? But what will be the width of this y2? So this will be equals to bw plus 2hw less than or equal to bw plus 8hf, remember. And in this case you will use the equation for C, this one, clear? And also remember, this is very important, okay. We will also use a concept, I do some example on it, okay. Sometime we divide this section with this option. Here you see y2 is this one and x2 is this one. But remember, if you are using this one like this one, if this y2 is greater than let's say this distance is greater than this one, so then this will be y2 and then this will be x2. Remember, this is very important, okay, this is very important. And then remember, in that case this one will become our y1 and this one will become x1, clear? So here we have two sections, one this one, this one. So you have to multiply this with 2 and this one will be different. So this portion will be used for these two and this portion will be used for this one. Clearly, similarly the case is here, clear? Here you see we have this section and here we can see this is our section. Similarly here you see the full one, clear? So this is x1 section, this is 2 section. So we will calculate, here we have two options, clear? So we will calculate C for this option and this option, and then the maximum value will be selected. Similarly here we have two options and the maximum value will be selected. Here is the example. Let me do some example on it. It is very important to understand. If you basically watch those videos. Basically here I explain this C. Okay, I explain this C because this C is also used in DDM method when you are using a DDM method with a beam slab supported system. So this is an H beam and you see option A, option B. Okay, what the difference between these two sections? You see here is, okay, this one. Here we have one section and here we have two sections. But here you see that the section is changed. This is section 1 and this is section 2. Clear? Now here this is the longer side, so this will be denoted, let's say, by Y, and this is our X. And here you see this is Y and this is X. Similarly here this is Y, clear, and this is X. And similarly here this is Y and this is X. Okay, I see many students do not calculate the value of C because they are confused. This is very simple. You have to maximize the value of C because C contributes the importance of transverse member. It basically increases the stiffness of a member. Clear? Similarly, in T section we have option A and option B. Here you see we have this section and this section with dot 1 and slash 1, and here you see slash 1 and dot 1. Okay, so short direction and for long direction. So both section, remember, for H beam, okay, this is for this option. Okay, so you see 0.636.5 divided by 29.5. This is used for yes, 29 for this one. Okay, X, Y, clear? And the next one, this is the formula plus the lower one, this one, clear? And then the C, which is basically calculated from this option, is this much, and from the second option is this much. So we'll use the maximum value and that will be this one, clear? Similarly for T section, you see for one option we got the C value is this one, and for other option of the T section we got this one, so we'll use this one, clear? This is very important to calculate the C value for both options, clear? But remember, mostly for if you have a T section, this kind of option, this is option B, give us the maximum C value. Okay, and similarly this one will give us the maximum C value, clear? And the next example is this one. For example, if you have a column capital, okay, this is the example is basically I choose this example from Wang book. I already show you this book, okay, this one I think so, this one. Okay, this is very important and it very nicely explain the concept of this C concept. Okay, so here you see we have an example. Okay, we have a drop panel, a column capital, and similarly we see a drop panel and a circular column and a column capital, 18-inch dia. The column capital width is 4 feet 6 inch and the column capital width is 2 feet and 3 inch. Here you see the column capital is in circular shape, 5 feet dia, and here you see this is 7 feet and here you see 8 feet and 4 inch. In this direction the span length is 25 feet and in this direction is 20 feet. You see the section, the beam section. Okay, this is our beam section, clear? This is our beam and this is our slab, clear? So 35 inch is the projection basically of the column capital. From central line it is projected 2 feet 3 inch and the column size is 16 inch. Okay, 16 inch square column on boundary, 18 inch circular column basically which is used in inside, and 18 inch circular column, 14 by 24 inch are the H beams. Okay, the width of this beam is 14 inch and the depth of this beam is basically from the top of the slab to the depth is 24 inch. Clear? So this is the total detail of this diagram. Clear? I think so. I have the section. Okay, this is the example. Clear? 16.3. Yes. Okay, you see this is the slab system and the detail. Okay, the whole detail. Clear? So if you have a column capital drop panel, how to calculate the value of C? It is also very interesting. So in this case, how to calculate the value of C? So the same case is here. Okay, we have to calculate the H beam. So from where this 51.5 comes, and you see the complete explanation from where 35 come and where is 51.5 inch. Okay, and the rest of the things are simple. Okay, and 35 inch is basically half of the column plus distance between center line of the column to the inner edge of the square capital. Clear? And you see it is basically this distance from the outer face of the column to the column capital. Okay, and this is 2 feet and 3 inch. This is 16 divided by 2. Okay, so all these things are add up and they got the value of 51.5 inch. Clear? So half of the column plus distance between center line of column to the inner edge of the square capital, mean that this distance, this one, and that is 2 feet and 3 inch. Okay, so 2 feet and 3 inch plus this distance, that is 16 divided by 2, it will give you 51.5 inch. Clear? And then as we have two options, one option is this one. Okay, section 1, section 2, and similarly with this option. Okay, here is the section. So as we did the calculation, okay, for this option, you see here we got this higher value, so the calculations are same. Clear? C for one option and C for other option. So this one is the maximum value, so use this one. Similarly, now for interior, we have also an interior. Remember, this is a little bit tricky. Okay, here, okay, they are using basically the thickness of the slab is 7 inch. I think so. In this example, the slab thickness here is, I think so, it is 7.5 or 7 inch. But as here, okay, here in this region and here in this region, it is around about 8.5 inch. So the thickness is more in the column region, but the thickness is smaller in the panel region. So that's why we will be using a little bit average thickness of the slab. So this concept is basically explained here. For the short or long interior beam or wetted slab, thickness of 8.5 inch is used. Clear? And the assumption that 1/3 of the span has a thickness of 10.5 inch and 7.5 inch. Basically, we use the wetted slab thickness. And how to calculate the wetted average? So you must know, okay, because they use the assumption, because they I already explained in this figure that the thickness in this region, that is 8 feet in 4 inch and 7 feet in this direction, it is basically here is 10.5 inch. Similarly in this region, but in the panel region we have 7.5 inch thickness. So they assume that, let's say, 1/3 means that one portion has a slab thickness is 7.5, but the rest having a slab thickness is 10.5 inch. So on the basis of that, they are using the wetted average thickness, that is 8.5 inch. Clear? And the rest of the section you will see here, this is the slab thickness. Clear? Shorter, longer interior beam. Clear? And the C is calculated here. Clear? This is the formula. So I think so the calculation is simple, but you have to just know the way. Because if you see here in this example, okay, this is the width of the section. Now remember, we have a different thickness in this region and a different thickness. So we just, what we did basically, we convert that total thickness into one equivalent thickness or average thickness, and the width is that one, that is 4.43 times this one. Remember why we are using this thickness. We are not use uh, uh, this width, okay, 8 feet 4 inch. Okay, we are not using this thickness because the transverse beam in this direction, so that why we have to use this one. Okay, because we are calculating the C value for this section, okay, for this section. So that why they are using this 4 feet and 6 inch. Remember, clear? Not here, here, okay, because the transverse beam running in this direction, this is our span direction, okay, this is our span direction, but the transverse section will be in this direction. Clear? Or if I show you the figure which I already show you here, I already explained that you will learn the concept in examples, okay. Like in this case, you see, we have a column capital, we have a drop panel, and we have a slab. Here the thickness is 7.5 inch, but here the thickness is 10.5 inch. So we are using just average thickness, that is 8.5 inch, okay. And remember, this is our span direction and this is our transverse direction. Clear? This is our transverse direction. So we have to use this section. We have to use this section. Remember, this is very important. We convert this complex system to a simple slab system in this shape. The thickness is average, that is 8.5 inch, and the width is, you see here, the width is this one, 4 feet and 6 inch in this direction basically. So this is the way that how to calculate the value of C in column capital case. Clear? This is the procedure. Here you see that how they basically calculate that feet is converted into, okay, so 53.2 inch is the section, and remember, this is now our y value and this is our x value. So calculate C value for this. Clear? And the whole theory is here, okay. This is the whole calculation, and in this case our C value will be this one. So you see the difference, here we have C, but this C is for this edge line. Remember, for this edge beam the C value will be that one, but for the center span the C value for this transverse section will be that one, okay, this one. So this is the difference. Clear? Similarly, from that book, if you see the example 16.3.3, so in that case, for example, you have edge beam, okay. Wang book calculates C for both short and long direction, okay. So this is short direction, I think so, sorry, this is short direction and this is long direction. So as you see in this example, that remember, there is no beam, but we have to assume, we have to imagine a beam, okay, which is exist in this direction and similar in this direction, because a transverse section must we have to for example, let's say if you have a slab system, okay, and you have a column. Clear? You have a column. Okay. If you have no beam right here in this edge portion, so you have to consider an edge beam, remember, and the width of that edge beam will be equals to the to the to the width of that column in this direction, remember. And then in this case, this will be the section of our transverse beam, this one. Okay, so the same case is here. You see in long direction in this way, the this one will be our transverse beam, and its this direction will be 10 inch because the column size in this direction is 10 inch. Clear? And this one will be the thickness of the slab. Clear? So this is X and this is Y for long section. Similarly, for short section, you see here in this direction, so a beam will be assumed and its width will be equals to the size of the column in this direction. So you see here we have 12 inches. Actually, no actual beam were used, but here we will consider an imaginary beams whose width equal to the column width C1. So C for short beam and C for long beam. Clear? This is very important concept. Okay, this is the example. Okay, there are no edge beam. You see, no edge beam, but still we are considered that there is an edge beam, and the size of that edge beam is equals to the width of this column, and the depth of that beam will be equals to the thickness of the slab, and the column size you see here. So this is our longer side and this is our shorter side. So in shorter direction, the width of the beam will be equal to 12 inches, but in shorter direction, for longer direction, the width of the beam will be 10 inch and the depth will be 5.5 inch. But for shorter, the width of the transverse beam will be 12 inch and the depth will be 5.5 inch. So this is all about the value of C, how to calculate C and what is torsional constant. In next lecture, inshallah, we will cover the distribution factor and then we will reach to our method. Clear? Now let me show you the basic concepts, okay, which is explained here. The same thing, a 3D frame system, we have to extract a 2D frame system from a 3D frame system. Okay, this one here you see the slabs. Okay, and those slabs will be converted into a 2D frame. Okay, this is our slab beam. Okay, if there is any beam, so that beams and slabs will be modeled only one member. Clear? Here you see this is the 2D frame, and then once we convert that 3D into 2D, okay, here basically our equivalent frame method is wind up, remember. Okay, so these are the equivalent stiffnesses. Okay, and we will determine the stiffness for the horizontal member and we will determine the stiffness for the vertical member. So the vertical member stiffness will be denoted by KEC, while the horizontal member stiffness will be denoted by the KSB, that is slab beam and equivalent column. Clear? And okay, this is the section. Basically then we will consider one section like here. Okay, and we assume that the beam, the columns are fixed in the mid portion of this story, and similarly half of the column of this ground story and far ends of the columns will be fixed. Clear? And similarly then, as this is the interior frame, so that interior frame whose transverse length will be equals to L2 and the span length will be equal to L1, and then we will start the analysis procedure. So how to calculate Ksb you will see inshallah in the example, because we will use these tables in examples, And similarly, these are the concepts. Okay, ISB determination, I already explained this, that if you are going to calculate ISB in a beamless slab system, so this will be your section. If you have drop panel, so then this will be your section. If you have a beam, so you will use a T-beam section. Clear? And you also see the concept of this equivalent column. Clear? And I will show you this calculation in example, because at this stage it is difficult for you to understand. Okay, and I will see you in example that how to use these tables, how to interpolate the values from these tables. Clear? And this is already explained, which is basically used for C. Okay, to calculate the value of C. So if you have a drop panel system, if you have a beamless slab system, if you have a column capital with drop panel, which section you have to choose? What will be its thickness and what will be its width? Clear? So I already did some examples on it. Clear? Similarly, in a beam slab system, okay, this one will be C1 and the transverse one will be the C2. Okay, and yes, I already explained this term. Okay, and this chart is also explained. Clear? And this is the final stage. Finally, using the flexure stiffness values of the slab beam equivalent column, a 3D can be converted to a 2D. Clear? After you calculate the value of Ksb and Kec, this will wind up the equivalent frame method. Clear? After that, you will use the moment distribution table or moment distribution method and find the values of moments. Okay, find the values of moments in all frames. Clear? In all frames, and then draw the shear force and bending moment diagram. Okay, so I hope this discussion will be a little bit boring for you people, because it is difficult to understand, but you must repeat these concept. It will help you in examples, and you must watch those lectures. You must understand the DDM method. Okay, because without a DDM method it is difficult for you to understand the equivalent frame method. See you in next lecture. Thank you for watching.